Let me correct a mistake most developers make on day one. Blob Storage is not a cloud file system. There are no folders, no file system hierarchy, no path-based navigation the way you think of it on a local disk. There are containers, flat namespaces, and inside them are blobs with names that can contain forward slashes to simulate folder paths. The forward slash in a blob name is just a character, not a real directory separator. The Azure SDK shows you a virtual hierarchy as a convenience, but the underlying structure is flat. This distinction matters for performance and design. If you have 1 million files and you query by prefix all files starting with uploads/2024/Azure handles that efficiently because it is a flat key value lookup with prefix scanning, not a directory traversal. Design your blob names with this in mind. When do you use blob storage? Anytime you have unstructured binary data at scale. User profile photos, product images, video files for a streaming service, application log archives, database backup files, machine learning training datasets, static website assets. If it is a file that needs to be stored and retrieved without complex queries, blob storage is almost always the right answer. What you do not use it for, relational data, complex queries across fields, or scenarios needing ACID transactions. That is what SQL and Cosmos DB are for. Azure gives you 3 blob types and choosing the wrong one is a mistake you cannot fix. You cannot convert a blob from one type to another after creation. Block blobs are the default and what you should use for almost everything. They are optimized for uploading large amounts of data efficiently using block-based parallel uploads. A block blob is uploaded in blocks, chunks of up to 4,000 megabytes each, which Azure then commits into a final blob. This makes parallel upload of large files extremely fast. Video files, backup archives, images, any general-purpose file, block blob. Append blobs are specialized for write-once, append-only patterns. You can only add data to the end of an append blob, you cannot modify existing data. This makes them ideal for log files and audit trails where you need a continuous stream of data written sequentially. Writing from multiple clients is safe because Azure serializes append operations. If your application writes logs to Azure Storage, append blobs are the correct choice. Page blobs provide random read and write access in 512-byte aligned pages. They are the storage backing for Azure Virtual Machine Managed Disks. When you create a VM, its OS disk and data disks are page blobs. You generally do not interact with page blobs directly in application code, they exist to back managed disks and certain legacy storage scenarios. So practically, if you are writing application code, always start with block blobs. You will only touch append blobs if you are building a logging system, and you will almost never create page blobs directly. Container and blob naming directly affects how you query, organize, and secure your data. Design it wrong up front and you are refactoring its scale later. Container names follow strict rules, 3 to 63 lowercase characters, letters, numbers, and hyphens only. No uppercase, no underscores, no periods in most contexts. The name must start and end with a letter or number. Your storage account can hold up to 5,000 containers, which is far more than most applications need. Blob names can be up to 1024 characters and can contain any Unicode character including forward slashes. Those forward slashes create a virtual folder hierarchy in the Azure portal and SDK. A blob named uploads/2024/05/user123/photo.jpg appears in a virtual folder structure in Storage Explorer, but the underlying name is the entire string. When you list blobs with a prefix of uploads/2024/05/ you get all blobs in that virtual month folder efficiently. The prefix design pattern is the most important naming decision. Use a consistent prefix structure based on how you query. If you frequently query by date, listing all logs from a specific day, put the date first. If you query by user, listing all files belonging to a user, put the user ID first. Azure lists blobs alphabetically by name, so your query pattern should determine the key order. Container access levels control public visibility. Private means all access requires authentication. This is the correct default for production. Blob access level allows anonymous read on individual blobs but not listing. Container access level allows anonymous read and listing of all blobs. Never use this for anything sensitive. You already know the 4 tiers exist. Let me tell you what developers actually get wrong when using them. The biggest mistake: treating access tiers as account level settings only. You can set the tier on individual blobs, not just the whole account. This means a single container can have some blobs in hot, some in cool, and some in archive, based on when each blob was last accessed. This granularity is what enables real cost optimization. The math that changes your thinking: archive costs roughly 20 times less per gigabyte than hot. If you have a terabyte of data that is never accessed, old backups, compliance records, decommissioned datasets, keeping it in hot costs around $20 per month. Moving it to archive costs about $1 per month. That is $19 saved per terabyte per month, with no change to your application logic if you set up lifecycle policies correctly. The retrieval costs catch people out. Archive blobs are offline, they must be rehydrated before you can read them. Standard rehydration takes 1 to 15 hours and costs per gigabyte retrieved. If you are rehydrating archive blobs frequently, you are defeating the purpose and paying more than hot would have cost. Archive is for data you keep for regulatory compliance and never expect to read. Cool and cold have early deletion penalties. A blob stored in cool for less than 30 days is charged as if it was there for 30 days. Cold has a 90-day minimum. Do not put frequently cycled short-lived files in these tiers, only data you genuinely plan to keep. Let me cover each upload method so you know which to reach for in each situation. The Azure Portal storage browser is fine for manually uploading a file during development or investigation. You navigate to a container, click Upload, select your file. There is no reason to use this in any automated or production context. The Azure CLI is good for scripts and one-time operations. The command is AZ storage blob upload, with the file path, container name, and account name. Add overwrite to replace existing blobs without error. For multiple files, AZ storage blob upload batch uploads an entire local directory to a container in one command. Useful for initial data loads and deployment scripts. For application code, use the Azure SDK. In Python, instantiate a blob service client with your connection string or managed identity credential, get a container client, then a blob client for the specific blob. Call upload_blob with your file data or a stream. The SDK handles retry logic, chunked uploads for large files, and content type header detection automatically. For large-scale data migrations, moving hundreds of gigabytes or terabytes from on-premises to Azure, use AZCopy. It is a standalone command line tool specifically designed for high-throughput blob transfers. It uploads blocks in parallel, uses all available bandwidth, and supports resumable transfers so a failed upload picks up where it left off rather than starting over. If you are migrating a data lake or seeding a storage account from an on-premises share, AZCopy is orders of magnitude faster than the CLI or SDK. Every blob has a URL in the format accountname.blob.core.windows.net/container/blobname. Whether that URL is accessible depends entirely on how you have configured access. If the container is set to private, the correct default hitting that URL returns a 404 or 403. Nothing is readable without credentials. If you have made the container or blob public, that URL is accessible to anyone on the internet without any authentication. Never make containers public unless you are intentionally serving public content like a static website or public download. Account keys are the root credentials for a storage account. There are 2 keys so you can rotate without downtime. A key gives complete access to every piece of data in the account: read, write, delete, list, modify permissions. Treat account keys like a database root password. They should exist in Azure Key Vault or environment variables managed by your deployment system. They should never appear in source code, config files committed to Git, or application logs. Connection strings contain the account key encoded in a longer string. They are slightly more convenient but equally dangerous. The moment a connection string appears in a GitHub repository, public or private, assume it is compromised and rotate the key immediately. Managed identity is the correct approach for production. Enable System Assign Managed Identity on your app service, Azure Function, or AKS pod. Grant that identity the storage blob data contributor role on the storage account via Azure RBAC. In your code, use default Azure credential from the Azure Identity SDK. Azure handles token acquisition and refresh invisibly. No secrets stored anywhere, no rotation required. A shared access signature is a URL with a cryptographic signature appended to it that grants specific, time-limited access to a blob or container. The signature proves the request was authorized by someone who had the account key or Azure AD credentials at the time the SAS was generated. The most important distinction is between Service SAS, Account SAS, and User Delegation SAS. Service SAS is scoped to a specific container or blob. Account SAS can grant access across multiple services in the account. User Delegation SAS is signed using Azure AD credentials instead of the account key. This is the recommended approach because it is backed by intra ID rather than a static key. Generate SAS in code by creating a SAS permissions object specifying exactly what the holder can do: read only, write only, read and delete, etc. Set an expiry time, and call generate_SAS on the blob client or container client. The result is a URL that works until expiry without any further authentication. Common use case: a user uploads a file to your API, and your backend needs to give the user a temporary URL to download the processed result. You generate a read-only SAS on that specific blob with a 30-minute expiry and return the SAS URL to the user. They download the file directly from Azure without your API server proxying the bytes. This reduces your egress cost and your server load simultaneously. The critical limitation: you cannot revoke an individual SAS token. Once generated, it is valid until expiry. If a SAS token is compromised, your only options are to rotate the account key, which invalidates all key-based SAS tokens but disrupts other services, or wait for expiry. Keep SAS expiry time short. Minutes to hours, not days or weeks. Lifecycle management policies are the most underused cost-saving tool in Azure Storage. They run automatically every day and apply your rules without you touching individual blobs. A policy is a JSON document attached to a storage account. Each rule has a filter section, which blobs it applies to, and an action section, what to do. Filters can target a specific container, a blob name prefix, a blob type, or combinations of all three. Actions include tiering to cool, cold, or archive, and deleting blobs. The trigger condition is time-based. You specify the age in days since creation, last modification, or last access. Last access tracking is a feature you enable on the account. It has a small cost overhead but enables more intelligent policies based on actual usage rather than just creation date. A complete policy for an application log system looks like this: blobs in the logs container move to cool after 30 days, move to archive after 180 days, and are deleted after 365 days. You write this rule once. From that point, every log file Azure ever holds is managed automatically. The oldest logs are cheapest, the newest are fastest to access, and nothing accumulates indefinitely. For blob versioning, add a policy action targeting previous versions rather than current blobs. Delete previous versions older than 90 days. This prevents version history from growing without bound, which can significantly increase storage costs for frequently updated blobs. One important note: policies run daily but are not instant. A blob that crosses the age threshold today may not be transitioned until the following day's policy execution window. These three features form the data protection layer for blob storage. You should understand them before you have a production incident, not after. Blob versioning creates a new version every time a blob is overwritten or modified. The current version is what you read normally. Previous versions are immutable snapshots you can access by version ID. If an application bug overwrites files with corrupted data, you can restore the previous version without any data loss. Versioning is enabled at the storage account level and applies to all blobs in the account. Soft delete protects against accidental deletion. When soft delete is enabled, deleting a blob does not immediately remove it. It is marked as deleted and retained for a configurable period between 1 and 365 days. During that window, you can undelete it. After the retention period, it is permanently removed. The cost is the storage space for retained deleted blobs during the retention period, typically minor compared to the risk mitigation. Container soft delete extends the same protection to containers. If an application bug or a misrun script deletes an entire container, you can recover it within the retention window. This is the safeguard against catastrophic data loss from operational errors. Point-in-time restore allows you to restore blocked blobs to the state they were in at a specific past timestamp. If your account had a ransomware event or a large-scale accidental delete, you can restore the entire account or specific containers to their state before the incident. It requires blob versioning and change feed to be enabled, and the restore point must be within the configured retention period. For production data stores, enable all three: versioning, soft delete, and point-in-time restore as a baseline. Let me close with the patterns you will actually implement in production systems. Static website hosting is one of the most cost-effective patterns in Azure. Enable it on a storage account, and blobs in the $web container are served as a website at a public URL. Your React build output, Angular app, or plain HTML site costs almost nothing to host this way. You pay only for storage and egress, not for a managed hosting service. Add a custom domain and Azure CDN for a production-grade static site at a fraction of the cost of app service. Azure CDN integration with Blob Storage gives you a content delivery network with edge nodes in over 60 global locations. You point the CDN at your storage endpoint, and requests from users around the world are served from the nearest edge node rather than from your storage region. For media files, product images, or downloadable assets with global users, CDN integration reduces latency dramatically and cuts your storage egress costs because CDN to user traffic is billed separately. Azure Data Lake Storage Generation 2 is Blob Storage with a hierarchical namespace enabled at account creation time. This single feature transforms the account into a true big data storage layer compatible with Apache Spark, Azure Synapse Analytics, and Azure Databricks. ADLS Gen 2 supports POSIX-style access control lists and performs directory operations atomically, both critical for analytics workloads. If you are building a data platform, decide at account creation whether you need ADLS Gen 2. The hierarchical namespace cannot be enabled after the fact. The blob trigger pattern with Azure Functions is powerful for any processing pipeline. A new file lands in a container, a video upload, a CSV export, a sensor data file, and a function fires automatically within seconds. No polling, no scheduler, no message queue required for simple cases. The function processes the file and writes results to another container or a database. Think about this before looking at the answer. Two distinct phases: active access for 60 days, then pure compliance retention for nearly 7 years. Hot tier for the first 60 days, receipts are frequently accessed for order queries and customer support. After 60 days, access drops to near zero, but compliance requires retention. A lifecycle policy handles the rest automatically. Move to cool at 60 days, cheaper storage, higher retrieval cost, which is fine since access is rare. Move to archive at 180 days, the receipt will almost never be accessed but must be retained. Delete at 2,555 days, 7 years from creation. You write the lifecycle rule once. Every receipt in your system is managed correctly from that point without any application logic changes. Active recall, reasoning through cost optimization scenarios like this is exactly what Azure certifications and architecture reviews test.